Welcome back to Anthro 1, Intro to Physical Anthropology. I'm David Leitner, I'm your instructor. Today, how old is it? How do we know how old fossils are, or geologic strata, anything from the past? How do we know how old it is? Especially because most of these things predate calendars and clocks and that sort of thing. So how can we possibly know? Well, that's what we're going to talk about today. So, the question itself is actually not a simple one. It sounds simple, but when you ask how old something or someone is, you're actually asking one of two questions. You can answer the question either, well, let's say, how old is Bob here? Well, we can answer it one of two ways. We can say Bob is 55 years old. Okay? Or we can say Bob is older than his son, but younger than his father. Both are very legitimate ways to answer the question, even though we might have an instinctual sort of desire to answer the first one. The fact of the matter is we may not know Bob's birth date, so we wouldn't really be able to say he's 55 years old. We'd just be guessing. On the other hand, we know that fathers have to be older than their sons and younger than their fathers, so that means that we can say this with a relative degree of certainty. Then, if we know how old Bob's son is and Bob's dad is, we can say Bob was born between these years. Hope that makes sense. The same is true when we're talking about dating fossils or layers of rock or whatever. The first would sort of relate to chronometric dating. The second would relate to relative dating. And if you need a way to remember the difference, relative dating is saying that Bob is older or younger than his relatives, even though we're using the word differently there. Relative dating just means you're dating the age of one thing in relation to another thing. The principles of stratigraphy help us a lot here, as I'll show in a minute. Chronometric dating, on the other hand, is using a calendar or a clock to say, it's like counting the rings on a tree, right? Something you know occurs at a consistent pace, and then you look for evidence of it to count how long it's been. Okay, let's talk about relative dating techniques first. Lithostratigraphy is the study of rock layers at different sites. Tephrostratigraphy is the study of layers of volcanic material, ash, lava, that sort of thing. And biostratigraphy is the use of index fossils and the principle of faunal succession in stratigraphy to establish the relative ages of a fossil. Now, in the first two, if you know the age of a layer of rock at one place, and you know that the rocks go in a particular order, and then you find the same order in another place, you can safely say that the age of those layers is the same as the layers in the other place. It's a little bit harder with volcanoes because most volcanic activity is more localized, but it's still working on more or less the same principle. You're going to date the age of anything in a layer based on which layer it's in and how old that layer must be. Biostratigraphy works on the same principle, but it's a little more complicated. Say you've got this unknown fossil in fossil assemblage B, which you find in this pink layer here. Okay? You know the age of all the fossils in fossil assemblage C, or of most of them. You know the age of the fossils in fossil assemblage A, and you know the age of the other fossils in fossil assemblage B, but this crazy looking thing you don't know. So, how do you tell how old this fossil is? Well, you look at the principle of faunal succession. We know that these cone-shaped shells only existed from this period to this period. And since we don't find any of them here, that's fine. We don't care. So let's just look at the fossils in assemblage B. Well, orange nautiloid shells show up from this period to this period. Wow, that's kind of a long period, so maybe we can narrow this down more. So obviously this had to occur at the same time that orange nautiloids existed, but we can narrow this down. What about with the stars? Well, the stars, the scallops, and let's call them oysters, the green oysters here, appear all throughout the stratigraphic layer. So they're not going to help us at all. We need to find something else to help us narrow it down. All we're left with are the blue nautiloids, like this one. Well, the blue nautiloid exists from this time period to this time period. Now we've narrowed down the age of this fossil. It had to exist when both blue nautiloids and orange nautiloids existed. And there's only one stretch of time when that occurred, and it's this period of time right here. That is the principle of relative dating. That is the principle of faunal succession, and the principle of index fossils and biostratigraphy. That's how we do it. That's how we tell the relative age of something, when we know the rough estimates of the ages of the other fossils. This can also be done with various chemical techniques. If we know the rough amount of time it takes for certain chemicals to decay into other chemicals, we can sort of compare them to each other. Then comes chronometric dating. We're going to talk about two main kinds of chronometric dating. First, we're going to talk about geomagnetic polarity, and then we're going to talk about radiometric dating, which uses radioactivity as the clock. Geomagnetic polarity uses a really interesting principle, though, and that is the fact that the Earth's magnetic field periodically reverses. Now, it doesn't do so like a clock. It's not like you can expect exactly every 1,131 years it's going to flip. No. It flips in a relatively random way, but when it flips that way, all rocks that form during that time are going to have the magnetic orientation of the Earth's magnetic field during that time. So they will be laying there with a magnetic field pointing in a particular direction. By measuring the pattern of those directions over time, we come up with essentially a pattern like this. So if we find a series of rocks that have this pattern right here, let's say we've got a long couple of long normal periods and then a long reversed period like this. We've got a pattern that we can compare this to. We look at this chart of all the different flips, and we notice it matches this period right here, so we know that these rocks are the same age as these flips. It's as simple as that. The reason this works is because the Earth's magnetic field is caused by a solid iron core at the center of the Earth. It is spinning rapidly, and as it spins, it generates a electromagnetic field. That is great, but while it's relatively stable, the fact of the matter is the currents in the liquid outer core, which are also largely iron, they are very turbulent, and periodically they cause the inner core to flip or to change direction. And you get these very unstable periods where the magnetic field will be constantly moving. And in fact, actually, we've been observing this for a long time. Magnetic north has changed a lot, even just in the past century. As this chart shows you, we've got some inferred positions of magnetic north from the 16 and 1700s in through the 1800s. And starting in the early 1800s, we've got what looks like a relatively stable magnetic north down there, where you see 1831, 1904, 1900. Come back in 1948, and things have moved northwards a lot. 1962, they've moved again. 73 again. So about every 10 years we're looking. And as we get closer to recent times, that movement is accelerating. Since 1970 to the present, the movement of the magnetic north has accelerated from just 9 kilometers per year to 52 kilometers per year. I know it doesn't sound fast, but you can see over time, this is several hundred miles. This is a lot. This is a lot. Does that mean we are necessarily about to go into a period of magnetic inversion again? It could be. But then again, maybe not. And we don't know when this happens, if it's a sudden thing in human terms, like it happens overnight, or if it takes years, or if it takes hundreds or thousands or even, tens of thousands of years. We know it happens quickly on geological timescales. We don't know how quickly it occurs on human timescales. But this is what happens during one of those reversals. Between reversals, you have a nice stable field, either with north at top and south at bottom, or flipped, where north is bottom, south at top. But in between, during the turbulence, you'll have these periods where actually you might even have multiple norths and souths. So, the interesting thing is how they discovered this. It was discovered by accident in the mid-20th century as they were exploring for oil in the mid-Atlantic, and they were taking magnetic readings over the mid-Atlantic ridge, and they noticed this repeating pattern on both sides that was exactly the same, where the polarity flipped on a regular basis. This is where they started. This is some of the evidence that supported the theory of plate tectonics and the movement of the continents. But it also then solidified this time scale that we can compare stuff to, this geomagnetic polarity time scale. Now, radiometric dating exploits the fact that the process of radioactive decay, although it's a random process, in fact produces a very predictable result. To take you back to high school physics for a moment, let's talk about isotopes. Isotopes are versions of an atom that have the same protons but a different number of neutrons. Sometimes these isotopes are stable, meaning they are fine staying in that configuration. Other times they're unstable, meaning they want to give off something and get rid of the extra mass there. When they do this, we call it radioactive decay. In radioactive decay, an unstable parent isotope decays into a daughter isotope, giving off heat in the form of an alpha particle, a beta particle, or a gamma ray. This daughter isotope will now be a different atom, either a different isotope of the same atom or an isotope of another atom. The amount of time it takes for half the original amount of parent isotope to decay into daughter isotopes is known as the half-life, and it's very predictable. So as you can see here, as the parent isotope decays, the amount of daughter isotope increases proportionally. So once you have half of the original amount of parent isotope, we'll call that time interval 1. Okay. Well, it will take the same amount of time for the half of the remaining parent isotope to decay as well. And at the same time interval again for another half to decay. So as you can see, regardless of the amount of time it takes for half to decay is a half-life. It is the same amount of time every time. So I want to show you a video now, actually, to kind of demonstrate this process, to maybe help sort of wrap your head around it a bit. The idea here is that even though each individual event, the radioactive decay, is random, taken together, because of the law of large numbers, they will even out into a very predictable curve that we can use. So let me show you.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 136. It's on half-life and radioactive decay. To model that, my daughter and I started rolling some dice. We had 32 dice in the cup, and what she would do is she would roll the dice, and then she'd pull all of a certain number out. So in this first simulation, she's going to pull all the ones out. And so you put those to the side. That's generation 1, and now generation 2, and generation 3, and generation 4. Now when you get to the 4th generation, she's hit her first half-life. What does that mean? Well, if there were 32 to start, that's the amount of time it takes for half of those to decay. And so that would be 16. So 16 have decayed right here. So she's going to keep doing that. And so if we watch what happens in the rest of the simulation, you're not pulling as many dice because there's not as many left, and eventually they've all decayed after 19 generations. But what you can see is that the half-life is consistent. So this was to 16, and then to 8, and then to 4, and then to 2, and then to 1. And so radioactive nuclei will decay. What does that mean? They're going to kick off some kind of a particle. It could be alpha, beta, or gamma. And then they're going to form a new, usually more stable nuclei. And so in this radioactive decay, mass and energy are conserved. We've talked about that in previous videos. But what we're going to talk about here is what is the probability of that decay occurring? Well, it's chance. So we never know when the next one's going to decay, but what we can use is the law of large numbers to calculate the half-life. The half-life is the amount of time it takes for half of the radioactive nuclei to decay. In other words, if this represents all of the radioactive nuclei, that would be the time it takes for half of them to decay. Now we've got all these ones left, and so we'd have another half-life like that, and we can just keep going and going and going and going like that. And so there's an equation we can use to figure out how many are going to decay at each generation. And so delta N, which is the change in the radioactive nuclei, so N is going to be our radioactive nuclei, so the change in N is minus, because we're losing those nuclei, so negative decay constant, I'll get to that in a second, times N, which is the number of radioactive nuclei, times time. And so if we kind of work backwards for that, in this simulation here, our time was advancing one generation after another, and so that's going to be 1 each time. What was our decay constant? Well, it's 1 in 6, so it's a 1/6 probability that you're going to roll a 1 and that one's going to decay. And so we could model that. I'll just use a quick little spreadsheet to do that. So at time 0, how many radioactive nuclei did we have? Well, our N value was 32. So let me walk you through this formula. What is our time going to be? It's going to be 1. What's going to be our N value? It's 32. So 1 times 32. And then what's our decay constant? It's 1/6. And so it's going to be negative 1/6 times 32. So what is that value? It's going to be negative 5.33. Now if we look how many actually decayed, it's 6. But it's close, negative 5.33. This is what it would predict to be, and this is what we actually got with a really small number of dice. Now how do you do the next one? Well, what we have to do is we have to take that 32, these ones decayed, so we're going to take 32 minus 5.33, and that's my N value for the next generation. And so now what do? I go back to this formula again. So it's going to be T, which is 1, times my new N, which is going to be 26.67, times my decay constant, which remains constant, and so what I'm going to get is negative 4.45. Now, how does that match up? Oh, it's pretty close to this. So then we subtract that value like that, and we could just do this over and over again. So right here on the right is going to be what we would predict to occur. And this is what actually occurred in this little simulation. And the number of dice are so small compared to the number of nuclei in a sample. But if you look at my data, the green line represents the actual data that we find. The red line represents the predicted. And so you can see that it matches up pretty quickly. What would happen if we changed the decay constant? What if we changed it from 1/6 to 1/2? So how would you do that in the modeling? Instead of pulling 1s out, she's going to pull the 1s, 3s, and 5s out. So what's going to happen? Well, it's going to happen more quickly. So more of them are going to decay at each point, and so it's going to take less time for all of them to decay. In other words, our half-life has gotten much, much shorter. And so you should be able to calculate half-life. So how long would it be for half of them to decay? You can see it's going to be somewhere around 4 generations. And so when you look at a curve, the first thing you want to do is figure out how long does it take to go from 100 radioactive nuclei to 50% of that. And so if I look across here, it took 1 year for 50% of them to decay. So let's watch the next generation. So now we should go to 25. You can see it's consistent, 1 year, 1 year, 1 year. And so you could say for this perfect model, it's going to be a half-life of 1 year. But on a test, you're more likely to get something like this. Calculate the half-life decay of carbon-14. So if you're given this curve right here, we go from 100 to 50. So you count across like that. So this is 50% of the carbon-14. And then you just read the time on the bottom. So if this right here is 10,000 years, what is our radioactive half-life? It's around 6,000 years. But let's keep going. So now let's go down to 25%, and you can see it's around 12,000. And so it's pretty consistent over time. Now, each form of radioactive decay is going to kick off a different particle. Let's start with alpha.
That's enough for that. That's mainly what I want you to get from this. What I want you to really notice there are a couple of things. The individual events of decay are random, but when you have enough of those events together, they even out, they smooth out that curve very easily. The other thing is, I want you to notice that the predictability of the half-life is very good in those first few half-lives, okay? But after about 5 or 6, you notice on his chart, the curve starts to flatten out. And the difference between one half-life and the next, the amount, starts to get so small that it's hard to tell when you've hit the half-life or not. And you even notice with his dice, sometimes he would get like just a series of one die decaying, no dice decaying, one die decaying, right? That's especially true with small numbers, but when you're dealing with the very many half-lives, your accuracy goes down. So, anytime you have a radiometric date, you should expect there to be a plus or minus number of years next to it, or whatever period of time you're talking about. That plus or minus is the margin of error. That's how confident we are in that number. And you will find that for more recent dates, it's going to be much stronger. In fact, some very recent carbon-14 dates can be around, they can have margins of errors in the tens of years, whereas older ones can be in the thousands. So, so for any radiometric dating technique, there will be an outer limit to how old it can date something to be. For carbon-14, that comes out to around sort of between 40 and 70,000 years, depending on just how you're measuring it, but that is the case. Now, radiocarbon dating, I want to use radiocarbon dating as the example here. It's one of the most commonly used, but it certainly isn't the only one we rely on. For any radiometric dating system to work, you need to have a start to the clock. You have to be confident that there was a point in time that you can measure from. And in radiometric dating, in radiocarbon dating, it relies on the fact that proportions of different carbon isotopes in the atmosphere are consistent. Okay, there are 3 main carbon isotopes: C12, which is the most abundant and stable; C13, which is rare. Only about 1.11% of the carbon atoms in the world are C13. But again, it's a stable isotope. C14, on the other hand, extremely rare, but unstable. That's what we're going to focus on for our clock, C14. Now, we know this proportion has to be the same in the atmosphere, but how do we know if it's the same in a normal sample, in a biological sample? Well, we know that C14 is formed as cosmic radiation hits nitrogen-14 in the atmosphere, and through neutron capture, it forms carbon-14. Okay? All 3 isotopes are absorbed during the process of photosynthesis. So when plants are going about photosynthesizing, they're drawing in those carbon atoms in the form of CO2, breaking off the carbon atom to use and releasing the oxygen. So they will be taking in those carbon atoms in the same ratios as they exist in the atmosphere. That means the carbon atoms in their tissues will also be in the same ratios. So when an organism comes along and eats the plant, they will be incorporating those same carbon atoms in the same ratios into their own tissues. So as long as these organisms are alive, any C14 that decays will not affect the ratio because it'll be replenished as long as everything keeps eating or photosynthesizing. So that's the trick. We know that while an organism is alive, its ratios of C12 to C13 to C14 are the same. Once it dies, however, it stops acquiring new C14, and instead, that C14 will decay into nitrogen 14. All we have to do is pay attention to the ratios of C14 to N14 in that organism. And that will tell us how much or how long it's been since that creature died. Because that is how long the C14 has been decaying for. And we count it in half-lives. Now, C14 only has a half-life of 5,730 years. He said 6,000. It's roughly 6,000. It's exactly 5,730. If something's much older than 30 to 40,000 years, you start running into fairly significant margins of error. But that gets us to the last days of the Neanderthals and the first days of the Homo sapiens in Europe. So it's still extremely useful for studying the past. But if we're going to study something older than that, we need other forms of dating. I'm not going to cover every kind that we have. There's a chart in the book that I'll show you in a minute that has a number of different ones. I'm not going to go into detail, but I do want to point one out because it's a fairly interesting one. So carbon-14 dating relies on the radioactive isotopes in the fossil itself. Potassium-Argon dating, which I'm going to talk about, relies on the radioactive atoms in the strata that the fossil is in instead. So it's not analyzing the fossil, it's analyzing the strata, which is also an advantage if the fossil itself is very delicate or very rare. Potassium-40 decays into Argon-40 in potassium-bearing minerals like feldspar and so forth. During volcanic eruptions, argon gas is evacuated from the molten lava. Okay, so when it falls, there should be no argon atoms in it whatsoever. Any argon in that material later will be the result of potassium-40 decaying. So all we have to do is total up the amount of potassium-40, and we know how long it's been since that rock was formed, which tells us when that layer was laid down. Now, potassium-40 has a half-life of 1.25 giga-annum, that's billions of years, 1.25 billion years, and it's accurate out to 4.5 billion years, which gives us, a tool we can use for the entire history of the Earth, which is great. The weakness is its margins of errors are pretty significant, so you're not going to be getting down to decades with this. But for older dates, that's less important. You also need multiple samples, and it assumes that the distribution of potassium in the sample is homogeneous, that it's not more abundant in one spot than another, which is usually correct, but you need to confirm it. There are a related technique of Argon-40 to Argon-39 that also helps refine this and requires smaller sample sizes. But that gives you an idea of how you can sort of reset the clock based on something. But so the important idea here is every radiometric dating technique requires some sort of 0 point for the clock, some sort of starting point for the process in order for us to use the radioactive decay as a clock. This is the chart. There are a whole bunch of other techniques as well. I'm not expecting you to memorize all of these, but be aware of them. That said, thank you very much. I hope you have a better idea of how we know how old things are at this point, and trust me, this is going to come in handy later on in class. We are going to be talking about these kinds of dates in the future. So until next time, take care of yourself and have a great week, and I'll see you soon.